Thanks for joining us, everyone, for Josh's talk as he explores the intriguing question on whether LLMs can be explained. Josh has pored over the latest and greatest research, dug into his PhD roots in physics to draw parallels between the world of physics and the world of LLMs, and combined it with his own deep knowledge of data science to help shed light on this provocative question. Josh, over to you.
Awesome. Thank you, Kirti. Yeah, this should be fun. I'm glad this is called Can LLMs Be Explained and not How to Explain LLMs. One of those questions is a lot easier than the other one. This is going to be a little bit of a weird combination of literature review, maybe a little bit technical, some personal musings, some sort of, what do you call it? Some practical approaches. So I hope there's something in here for everyone, or either everyone will be equally annoyed by how I did it. So in any event, jumping over to slides, I think you guys can see my screen. Somebody stop me if this doesn't work. Cool. So welcome, Can LLMs Be Explained? I'm Josh Rubin, Director of Data Science from Fiddler. Cool. So let's just start with why explain AI? Like, what's the point of explainability at all? Explainability in machine learning aims to distill a model's behavior and present it in a format that's useful to human stakeholders. So, it's some combination of a human plausible thing with a sort of a technically precise thing, right? And it has to be useful. And a few benefits are, it can help identify weaknesses in a model's understanding of the relationships represented in its inputs. So that could indicate vulnerabilities to generalization in novel scenarios. Robustness is important, and the way that we use models sometimes, we're looking for unusual cases. We're trying to use them to identify things that are out of the normal. And so it's important that they're robust even in strange quarter cases. It can help domain specialists identify important features driving a model's output. So this is sort of the human in the loop use case. This is when a human being is having their own skills augmented by working with the machine. So it can help a human operator be more efficient in their decision-making and less prone to overlooking important details. It's super helpful to know the why in model reasoning. Building confidence that a model makes decisions according to desirable reasoning rather than bias that's reflected in the historical record or some other malfunction. I won't dive into bias too much, but there's no shortage of examples of models making inappropriate decisions just based on things that they've gleaned from human behavior as recorded by the internet. And we'd like, in most scenarios, for them not to be exhibiting those biases and how they're used. Okay, so understatement of the entire slide deck is, here we've got poll results. Can LLMs be explained? And it looks like we mostly like in some cases. I'm glad no one is in, or there's a few of you in the not ever camp, and there may be some scenarios where not ever is plausible. But I think in some cases, or not quite today, I'm kind of with the rest of you folks on where we are in this distribution. I don't think we're at totally yes. Great. Okay, so here's this slide. Models are getting complex. Understatement of the entire deck, right? We all know this. The point I want to try to make here is that complexity is different. Most traditional predictive machine learning can be thought of as function approximation at some level. Basically, it's like trend lines in Excel, right? Like you're interpolating and extrapolating around training examples, even if it's very multidimensional. Ideally, our models do pretty well at interpolations, and often they do badly at extrapolations. And that's most of the game, whether it's a regression or a ranking or a classification task. There's a lot of flavors and it gets complicated, but it's sort of curve fitting, right? So how is complexity different? Deep learning models are not just bigger ML models. So the most efficient approach to optimizing their training objectives we've discovered, and I'm including, this is all large deep learning models, isn't specifically a statement about LLMs per se. But But the most efficient approach to optimizing their training objectives is to learn complex abstractions. So for LLMs, this is the prompting paradigm. And, you know, we talk about this casually, but it's a pretty profound thing. We've talked about things like in-context learning, few-shot, zero-shot learning. It's not really even learning in the ML sense, right? This is causing models to make, know what to do based on what you've described to them. And you're entirely working in this language abstraction that the model has learned through a traditional training process. Pause for a minute. This is a really strange thing. We're not optimizing an objective when we've done this. We're just telling the model what to do. And it's part of what makes it feel magical, but it's pretty profound. They exhibit this characteristic called hallucination. It's a kind of an error. I don't know if it's a interpolation error or an extrapolation error exactly. I don't think we know entirely what that is. And so we kind of need to figure it out because it's on everybody's mind who's trying to operationalize these things. And then finally, are ML explainability tools even the right ones here? This is really a kind of profoundly different paradigm. So the shift to prompting in itself is an example of emergence. And emergence basically means a behavior that would be difficult to predict from the microscopic rules governing the system. The linear algebra of weights and biases being multiplied together and attention weights. You might not be able to anticipate that you would be able to describe a certain course of reasoning to a model via this prompting paradigm from those microscopic rules. The function fitting is easier to understand, right? That's the traditional motif. And if you'll I used to be a physicist, so you have to bear, this is my one self-indulgent slide on physics. So this is a phenomenon that we're actually pretty familiar with in the physical sciences. So systems with many interacting components lead to emergent properties. There's this phenomenology that emerges that isn't just naively the sum of the parts. And we need to study that and learn it in order to be able to do useful things with these systems. So examples of this might be things like sand dunes or flocking birds. Just knowing how friction works on a few grains of sand and the direction of the wind, in principle, is everything you should need to know from a kind of, purely reductionist perspective, from the pure mechanistic perspective, how the system works. And yet, there's clearly structure that emerges out of the interaction of all those many, many particles. I used to be a particle physicist, and I worked on proton structure a lot. And the most interesting part of that problem was that the proton's properties, like its mass, are not the sum of its parts, right? The quarks that make up a proton, if you naively add up their masses, you get about 2% of the mass of the proton. All the rest of that behavior is generated via emergent degrees of freedom that come out of a lot of components interacting in a simple way, which is pretty amazing. It's also the reason why when you're sick, you see a physician and not a physicist. One wants to see your organs, the other wants to see your atoms. You wouldn't be able to predict, or diagnose or treat a stomach ache based on the atom perspective, even though fundamentally the organs of the human body are just made of those atoms. So anyway, I'm done with the physical analogy, but I think that's the kind of chasm we're crossing here into large deep learning models, especially these like enormous, foundation LLMs. Is that there's something really new that's happening here. So here's a slide on impressive phenomenology. So results from May from OpenAI, and there they try to use a GPT model to summarize the activations of neurons of a smaller transformer model. So they feed it lots of examples that excite particular neurons in the system, and then they ask GPT-4 to give an explanation. So, this particular neuron is stimulated by references to movies, characters, and entertainment. You can then go back and pick a particular word in in an output and understand a lot of things, or try to understand a lot of things about, what the model is thinking by what's stimulated in it when it's doing its prediction. We had this amazing recent paper, October, from Anthropic, where they focus on the fact that neurons actually seem to be polysemantic. So there are actually many different levels of human meaning that are layered into even individual structural components in the model. So a particular neuron may participate in like dozens of different individual concepts. They use this sparse autoencoder to try to learn the concept basis the model's working on. They produce these amazing maps of the different concepts and how they relate in terms of their neighbor relationships. They also let you drill into specific content, specific concepts, and look at examples from them. So, and it's this beautiful like interactive thing. These are both papers that include interactives and should be played with. They're very impressive. But what do I mean to say here? So in both of these cases, these very formidable research teams are applying these techniques to very simple transformer models, like sort of like the simplest transformer, or some of the simplest transformer models, at least in the entropic case, that you can cook up. So it's fantastically interesting from an academic perspective, but we're all building applications out of GPT 3.5 and 4 and things coming in the future. And I think both of these teams have conceded that it's really hard to apply this sort of reasoning in the context of, full-size production-grade LLM. So our practice is way ahead of our understanding right now. We need to keep gathering this information so we can understand better. But I think this isn't a tractable explainability technique for practical purposes right now. So there was a nice review article recently by Zhou et al. Came out in September. They give this particular hierarchy of talking about explainability techniques. There's a bunch that are sort of what they call the fine-tuning paradigm. That's my sort of microscopic, sort of the traditional ML approaches. Things like attributions, Shapley, integrated gradients, even looking at attention vectors and things like that. The world we've entered, models are enormous. They're often proprietary. They have dozens of attention layers and heads. And that kind of microscopic reasoning may not describe the emergent reasoning that's happening in these systems. I think there are still some great corner cases where some of these tools are useful, but I'm going to focus for the rest of the talk on the prompting paradigm, which is sort of the emergent paradigm. So, let's study the phenomenology of model behavior, establish the rules in this domain. I'll talk about model confidence for understanding hallucinations, higher order attribution, and then I'll dive into like a sort of a thing about self-explanation. So here we go. This is going to be like the total other end of the spectrum from the Anthropic OpenAI research. This is two practical explainability strategies that we're playing with now in Fiddler. Here's one that's described in this recent paper by Xiong from June of this year. This has been an amazing year, where they look at consistency-based confidence. And so basically they define self-consistency confidence, like how much does a model's output vary if you just reword the same prompt? So same meaning on the input side, how much variability is there in the output? And can you use that to measure whether the model is rooted in some solid knowledge or whether it's just making stuff up? So the hypothesis is that if it's making stuff up, then there's going to be a lot more variability in its output. They also talk about induced consistency confidence. That's when you try to give the model a misleading hint in a prompt. Those two consistency-based techniques are certainly better than verbalized confidence and seem to work well for identifying places where the model's just making stuff up. And in fact, you may have attended Amal Iyer on my team, his workshop a little bit earlier on Fiddler Auditor. If you haven't, I direct you to take a look at the recordings of that particular session. So we've developed this open source tool that can do a variety of different kinds of evaluations, but one of them is looking at stability of model responses under lots of permutations of the input. So, here's a prompt, for a multiple choice question. Which of the following treatments has not demonstrated efficacy in BED? And Auditor runs through a whole bunch of perturbations using another model of the input. So just rewords them. And it looks at the changes in the model's responses and then does a cosine similarity measurement to look at the dispersion between those outputs to try to understand whether the model's reasoning is actually stable for that question. So there's some really interesting questions about like characterizing your model for different, sort of subgenres of content and understanding where it's most reliable. And that's what Auditor aims to solve. You can also do attribution-like explainability in RAG settings. So check out Murtuza Shahidwala, also a team member of mine, at 2:15. He'll be doing a workshop on how we built the Fiddler chatbot, or documentation chatbot. So I think we all know about RAG. This is retrieval augmented generation. When you ask a model to answer questions using documents retrieved from some more conventional document retrieval process. And what Moto's been playing with is, trying to measure which of the source documents have the most impact on the model's response. There's some reference generation, and then you can play this game where you regenerate using a lot of different variants of the references you provided, and try to look at what causes the largest deviations from the reference generation. Great, and now, so here comes my my sort of long story on self-explanation. I've really varied a lot on my opinions of model self-explanation. I'm going to start with something from a blog post. Feel free to check it out. I think it's actually pretty interesting. I played this game of 20 questions with ChatGPT, and I made it guess my clue, and so that was sort of interesting. It did a good job of figuring out what I was thinking. I decided to switch the tables and ask ChatGPT, this is GPT 3.5 Turbo, to let me guess clues that it's thinking of. And so here's the dialogue. Me, I would like you to think of an object, and what I'll ask you questions to try to figure out what it is. And it says, sure, I'm ready. I say, does it have moving parts? And it says, yes, it does have moving parts. And I say, does it use electricity? And some versions use electricity, but not all of them. And I ask, is it used for calculations? Yes, it can be used for calculations. And then I determine that it's a computer. So it's like the most basic game of 20 questions you could play. But I got curious whether the model had any clue what its clue was before the last turn. And so I reduced the model's temperature parameter to 0 to get it to be deterministic. I'm probably the only person who my favorite part of the OpenAI Dev Day keynote this week was when Sam Altman announced that you'll be able to give a random seed to the model and reproduce any generation that you want, because this was a real headache. So this allows me, by reducing the temperature to 0, I can reproduce any dialogue exactly. And I can branch the dialogue in different ways. So the dialogue you just saw is the leftmost branch here. And then I try interrupting it two different times before that at prior questions to ask if it's thinking of a computer. It wasn't thinking of a computer until the last step. So, it only decided the last term that a computer was the answer. The things I would point out here is it feels like a human, but don't presume that it thinks like one. It had no consistent plan. It's stateless and just predicting the next token. Like, we all know that, but we've trained these things to create the illusion that it thinks like a human. Would you expect it to be able to introspect reliably and self-explain? That would have been a really good poll question here, but I didn't think to do that. I think that's an important question. If it doesn't have state, can it actually introspect? And in fact, if you look at the Sparks of Artificial General Intelligence paper that came out of Microsoft Research along with GPT-4, they basically do an experiment, and they do a set of experiments, but they define these two things: output consistency. Does a model's self-explanation plausibly describe how it arrived at a result? And then maybe more importantly is process consistency. Does the model's reasoning about a particular example generalize to describe its output for other analogous scenarios? So in their words, it's often what humans expect or desire from explanations, especially when they want to understand, debug, or assess trust in a system. And I'm going to, just because I'm running short on time, I'll be kind of quick here, but basically they've asked the model to translate into Portuguese the phrase, "the doctor is here." The model comes back using the male form of "the doctor is here." And it explains that as being one of the professions for which the male is the default. And maybe that's how the world works. I don't know, but it's something that the model's learned. And then they ask it for some professions where it would use the female or the feminine article. And so it says nurse, teacher, secretary, and actress. So the researchers begin a new session. They ask it to translate "the teacher is here," and it again comes up with the male version, and it provides a different explanation there. So that's a failure of process consistency, right? It's not reasoning session to session in consistent ways. And so that indicates a problem. In January of 22, we had Wei et al. Who, on the kind of a reassuring end, we have learned that there are things you can do with chain of thought reasoning by giving explicit steps to the model that very much help rein in its ability to do complex reasoning tasks. So maybe there's some help there in terms of model understanding if we can, we can part out to simpler sub-pieces what it's supposed to do. In May of that year, last year, Kojima et al. Showed that, this is a cool name for the paper, large language models are zero-shot reasoners, right? They can make their own plans, and we can create two-stage generation and allow the model, they introduce this prompt, let's think step by step, which you may have heard before. That seems to work really well at letting the model generate its own prompts. And they do this kind of two-stage invocation of the model. It produces explanations that are more robust to changes of the input. So that's reassuring in terms of model reasoning. But then we have Turpin et al. From 23, from May, that find some pretty damning ways in which the explanations, even with this kind of chain of thought reasoning, may still be unreliable. So they deliberately bias prompts, and rather than the model explaining the bias that they've introduced in the prompts, the model seems to provide an answer, which is sometimes incorrect, and the explanation it provides seems more aimed to justify the decision it's made than to disclose the bias it was given. So it's not giving us the full picture. Okay, so I know I'm moving fast through this. I'm almost to the end of what I wanted to say. But still, there's other promising directions. So we're kind of going back and forth, like we're feeling this thing out. We're learning in real time. Here's Mukherjee et al. This is from June of this year. They've created Orca. This is a 13 billion parameter small model that learns from GPT-4's reasoning process. They use the think step-by-step style instructions to get GPT-4 to do to provide explanations with its answers. And instead of just training on questions and answers, they train on question-answer explanations. It helps Orca to significantly outperform similarly sized models by learning the reasoning from a much larger model. So here's an idea of my own that was sort of inspired by the last two things I mentioned. Sort of one, the unreliable explanations from Turpin, and then the Orca example. We know that we can use, human feedback to fine-tune models to make them behave very differently and align themselves very well with what we want. Can we deliberately inbuild alignment or fine-tuning to enhance faithful self-explanations and process consistency and bias disclosure? I think between the two previous papers, there may be enough ideas in order to create training sets where we can encourage model in one of these training processes, come up with a set of good examples, and maybe enhance their ability to self-explain. Even if it's not introspection formally, like humans think that humans do, we can certainly change their behavior in ways that make them behave more like humans. We've proven that before. So I think there's a new direction there. And then just down to conclusions. LLMs are sufficiently complex and they work in powerful abstractions. We need to learn phenomenology. This is going on right now. We're getting better at it. We're still learning, as with physical systems, that phenomenology is important. Self-explanation doesn't generally appear to be a safe technique. Use it cautiously and in task-appropriate ways. It may be, I would love to know if, aligning or fine-tuning for faithful self-explanation is possible, because I think there's a potential there. We already have practical techniques that we can use: consistency for model confidence, perturbation of inputs to RAG. And then finally, this has all shown that, comprehensive observability is more critical than ever when the explainability tools are weak. So, use feedback from humans or from other models to understand how your model performs, how well it performs, and where it fails. Quantify that. Do evals on your model on different data sets. So I think that's a really important theme, is just to be quantitative about understanding where your model performs well. And that's it. That's all I wanted to say. So thanks, everybody. And it looks like Kirti's queued up to sling a question.
Yeah, some good questions in here, Josh, and thanks. That was a great presentation. So the first question is, do you think humans are humanizing such models more than what they actually are? In other words, do LLMs have the same mental state like we do?
I don't think so. I would direct you to that blog post, the What's ChatGPT Thinking? Go Google search it, or find it on the Fiddler blog. You know, we know that they're stateless, right? They every forward pass is predicting one token. That might be part of a word, right? It might be a letter. And everything that is their state is in the chat transcript of what was asked of them and how they responded up until that token. We sort of coerce them into behaving like humans because we want to interact with human-like things. But I don't think, and so there's a danger there, right? I mean, we're sort of empathetic, sort of pack animals that have all learned to model the behavior of other humans that we interact with. I don't think that as, this is maybe a little bit philosophical, but I don't think that as a species, we're well prepared for something that acts like a human, but isn't a human. I don't think humans have encountered that before. And so I think caution is advised here.
Great. So we can do 2 more questions and we have about 2.5 minutes. So let's try to get through them. So is explainability the same as chain of thought reasoning? If not, what is the difference?
Explainability can take a lot of different forms, even in traditional ML. I mean, in so it's, I think the general umbrella goes back to that first statement about, explainability, trying to make model reasoning, the factors that are affecting the model's internal logic accessible to human stakeholders, regardless, and that whole concept may vary depending on who the stakeholder is. Maybe it's a model developer who's very technical. Maybe it's, a person at home who's just received a loan rejection, or their insurance company has said, we're not going to pay for this procedure that you just had according to this, some rubric of some, heuristic that a model used. So, it both, again, has to be faithful to the model's logic and to the human's logic. And so I think there are some kinds of chain of thought reasoning. Like, I think if you could create a model whose self-explanation was actually faithful to its process, I think that's a kind of explainability that's useful. And I think part of the theme that I was trying to get across is I do believe that the kind of prompt conversation space with the model is really a first class, it's not a hack, right? This prompt paradigm it's this emergent paradigm that's really different than the underlying ML. And so we have to get used to that, and we have to understand how to work with that. I don't know if that totally answered the question, but it was a good question for sure.
So in about 45 seconds, if you can, Josh, do you think reinforcement learning-based LLMs can maintain a notion of state?
I would again direct the asker of this question to that blog that I wrote. I try to reflect a little bit on what might be happening. I don't think it's madness to think that in the process of training a very sophisticated LLM, I think at some point part of this paradigm shift is all bets are off on abstractly what the model's learning and even how it persists information, how it regards its the context that it's passing in generating the next token. So I don't think it's total madness to think that there is something that the model could learn to regard, its prior context as some sort of state. But, you might be that, I don't know that I am the person who has the best answer to that, because there are certainly people who are very focused on the training process. I think it's actually a pretty deep question.
Josh, I do need to interrupt because we should start the next session.
All yours.
So sorry about that, but that was a great session. We have someone from the audience who has even said great work in summarizing a complex subject. So I definitely +1 that. Thank you.